Welcome to our second review for Physics 111. So I'm going to walk you through the material we are going to cover in the exam, just reviewing some key points. I'm not going to do that many examples, but hopefully these ideas will help you guide your study to the most important things you need to make sure you understand correctly. So let us do this then. Physics 111, the parts that we have covered in this course pertinent to this exam are parts of chapter 3, which is kinematics in 2D, chapter 4, which is Newton's laws, and pieces of chapter 5, most of chapter 5, not everything, but applications of Newton's laws. Okay, so let's start with chapter 3. So the most important concepts in chapter 3 are simply extensions of chapter 2. So let us review those. So definitions, key definitions. And these are displacement, which is a vector, delta x equals to x final minus x initial. So if you know two vectors, you know how to do this. If you are provided with vectors in, say, a diagram, then you actually are able to do algebraically this operation. Then we have velocity, phi, which is the displacement divided by the time interval, and acceleration, A equals delta V over delta T. Those are our key definitions. After we have the definitions, we are going to note that in chapter 3 we dealt with two important systems that show motion in 2 dimensions with features that we do not observe in motion in 1 dimension. So 2D systems. And these are projectile motion, and in a moment we're going to write something about circular motion with uniform speed, so uniform circular motion. Projectile motion is when, say, this is the ground and we throw something into the air, and we usually give it some initial velocity, and then we see it fly through the air and eventually perhaps land somewhere else far away. So that's projectile motion, and there's one key observation about this. This has the same physics as free fall, and then we state that its key feature is that its acceleration is constant, and this acceleration has magnitude g, which is the free fall acceleration. Remember that name. It has a name. It's not gravity. It's free fall acceleration, and also it points down. Okay. Now, when it comes time to write equations, we first set a system of coordinates, and this is the standard system of coordinates that is often used for these problems. Is the one the book uses, and in this standard system of coordinates, this is a piece of a parabola, and in this standard system of coordinates, your initial velocity might look like that. Typically, you're given the magnitude and direction of this vector. so that you're able to determine the initial components in the x direction and the y direction. So the key feature of this system is that the x and y components of the motion are effectively independent. So we can know what each component is doing by solving the pertinent equations, but other than their positions in x and y occur at the same time, they are not connected. You don't, after you know the initial velocity in x, after you know the initial velocity in y, you do not need to remember more of y to know x or more of x to know y. You can proceed independently. So in the x direction, we have that there's no acceleration, so that Vx is constant. And you can use the typical equation for constant velocity. In the y direction, Ay, now in components, is minus g. Remember that g is always positive. So the y component of acceleration is always minus, let us say, 10. And therefore, you can use the kinematics equations that are delta Vy is equal to Ay delta t, and the other standard ones that says delta y is equal to V initial in y delta t plus 1/2 Ay delta t squared. I'm running out of space, sorry about that, but you should know that equation. And Vy final square is Vy initial square plus 2Ay delta y. Just a couple more things. Remember that always the work is simplified when you identify certain features of special points. And this is a special point here at the top. At the top, we have that the Vy is 0 because it's not going up anymore. It was going up before, and then it's not going up anymore. Now it's time to go down. The velocity there in the y direction is 0. And using that condition in your equations allows you to typically determine whatever information you're seeking about that high point, that high point. Okay. Second system. The second system that we work on in 2 dimensions is the circle. Badly drawn circle, but a circle, or close enough. And in this circle, we're going to be traveling at constant speed. So you're always, I'm drawing vectors of velocity. And the interesting part about this system is that uniform circular motion. And in this system, the velocity is changing because it's a vector and changes direction. The magnitude of velocity is not changing. That we take that as a statement of what's happening. It is true in this context. We are looking at precisely that case when v is not changing. This might look strange, but see, what happens is that we are always going at the same speed in this track, but of course our direction is changing. If this is true, then A is not 0, and in fact we know more. We know that the acceleration always points towards the center of the circle. This is a construction that we did in lecture. So that's the second system. So again, in chapter 3, kinematics in 2D, we have these definitions and 2 special systems, projectile motion and uniform circular motion. Moving on, chapter 4. It's Newton's laws. A general overview of Newton's laws, and there are 2 things that we need to do here. We're going to describe what those Newton's laws are. The first law says simply that in the absence of forces, if nothing is happening to your object, in terms of forces, it's not interacting with any object, then its velocity is constant. This is a strange thing because we always think that to have an object moving, we need to keep pushing it. This is not correct. This is not intuitive, but it is true. The second law says that the acceleration is F net over mass, and in a moment we are going to discuss what is this force thing, and in lecture we discuss a couple different ways to think about the mass. Mass is the amount of matter in the amount of substance in an object, but also in fact is defined by this relation. So if you want to know the mass, is just the relation precisely between acceleration and force. However, once you know the mass of an object, then you keep using that information to keep relating the force and acceleration. And in a moment we'll describe some forces. The third relation, third Newton law, says that forces appear because objects interact with each other. And if that's the case, there should be a relation between the force that A applies on B and the force that B applies on A, and therefore, and then these two forces are related. They have equal magnitude, but we implement this direction relation with negative sign. This means that, of course, we have changed direction, so they have equal magnitude and opposite direction. Let us do a brief catalog of forces. What are forces? The forces that we have considered are gravitational forces. These are long-range forces, but in context, we usually look at this case. We look at something happening near the surface of the Earth, and hey, this is very far from the center of the Earth, so this is a long-range force. We think of the as if, and this is true, we can consider that as if all the mass of the Earth was concentrated at the center, and we are very far from it, but we still feel it. The net result is that the Earth pulls us towards the center, and when we are in the surface of near the surface of the Earth, this means that we are being pulled down. We call this force in context. In this context where we are on the Earth, this gravitational force then receives the name of weight. Further, we have a little bit more of information. This came out in chapter 5, but let us give it here. This weight is a strange thing because this is the second appearance of mass in our equations, in our relations, in our laws, but the weight is also proportional to the mass and is mass times the free fall acceleration. That's one type of force. The other type of force appears when we have a surface and two objects are in contact through that surface. So this object and this larger substrate, larger environment, so they are in contact at this region, and therefore when we have that, we generate forces because the presence of these other objects impedes motion, or at least makes it difficult. So in this direction, perpendicular to the surface, that's terrible. Let's do it again. Let's undo this, because that was terrible. So in this direction, the motion is impeded by the presence of the of that surface, and therefore this generates these contact forces is a normal force, acting on the box here. And the second one is that if we try to move this still maintaining the contact, then we're going to get a, if we are moving to the right, for example, or try to move to the right, we're going to get a force, a friction force. Okay, so those are the contact forces, normal and friction, and if it is kinetic friction, always points in the direction opposite to the velocity. There are a couple other forces. Let me mention that if we are pulling things, for example, with a rope, then you have a tension force. This is also a contact force, but because the shape and nature of this object, it has its own peculiarities, then we set it as a special type of force, and then we call it the tension. Okay. And that's it for the our catalog of forces. There are a few more, but you can review. For example, spring forces and drag. So not hard. Let us go to a new slide. And in this new slide, now we are going to talk about applications of Newton's laws. So this is chapter 5. And the scheme for applications is very similar in all cases. Let us mention then what we did. In the sections we covered in chapter 5, we had static problems where the acceleration is 0, and dynamic problems where it's not. Then we also review in more detail these ideas that I already mentioned about weight and apparent weight, and a little bit more about inclined planes and normal forces. So these are the main applications. In the applications, we always follow the following pattern. We have, we draw a diagram of forces and accelerations. Then we write equations of motion. And this is just Newton's second law, but adapted to the particular information we have. And then we work out components. And then we finish off the solution with whatever is needed. So typically this implies a specific, determining a specific value. So then solving equations. Solve equations. Okay, so let us give a quick example. This I did for those of you that came to an in-person review. So I'm doing also for all of you, whatever you're watching. So let us remember this exercise with the car that is being towed or pulled. And we quickly identify the following forces acting on our system. So I'm going to already abstract this guy here to a single point. But we identify that we have always some weight, W. The magnitude of that weight is going to be mg. The normal force, because it's on contact with the surface there. The since we are moving to the right, we probably are going to have some force of friction or drag. And finally, we see a tension there, so maybe a cable that is pulling us up. And then you have to be careful with doing the drawing because it has to reflect the relative magnitudes of the forces. But let's just put right now a small tension here. Probably want to do this one larger. Okay. So those are my 4 forces, and let's see what I wrote a moment ago. Aha, I'm done, almost done with my diagram. I need to have an acceleration. So the problem context will give you the acceleration. We are moving to the right, so we might have a case where where we are moving with constant velocity, in which case the acceleration is 0, or perhaps we are actually being accelerated, or we're slowing down. But if we are accelerated, speeding up, maybe we have then a horizontal acceleration. Let us write the equation of motion. By equation of motion, I mean simply the restatement of Newton's laws in ways that are adapted to the problem at hand. In this case, we are going to have that the net force is the sum of forces, and these forces are simply added as vectors. So even though we see things down or left, we don't care. We just add them up. So we have weight plus normal plus friction plus tension equals ma. That's it. And then we have the x and y components of these forces and of the acceleration. So we simply write wx plus nx plus fx plus tx equals to max, and wy plus ny plus fy plus ty equals may. Okay, so now we are going to do the spelling out of these forces in components. So we set a system of coordinates like so, x and y. And then the forces are like so: normal, tension, friction, and weight. And let us do a small table. So this is the x component, this is the y component, and these are the forces: F, N, weight, and tension. And then it's very easy to read some of them. Let's do the easiest one, is perhaps the normal force. The nx is 0 because look at that vector. It just points up. And the y component, in terms of its magnitude, if n, remember the magnitude is n, the magnitude is f, the magnitude is w equals mg, the magnitude is t. So we want to express all this in terms of the tension, in terms of the magnitude, which is usually the information we can use, or we are given, or we are after. So nx is 0 and ny is just the whole thing, the normal magnitude. Same with f. The only difference with f is that it points to the left. I'm sorry, this is wrong. It points to the left, so this is minus f, and it has a 0 y component. Then we have the weight. It's 0 in the x direction, and in the y direction is minus mg. This is where the negatives come, here at the f and here at the w, not before. Finally, the tension is the only one where you need to use the skills that we developed in the previous video. And there's my tension, has magnitude t, and look at that, there's a triangle there. So in that triangle we can read the components, the magnitude of the components Ty. It's okay, they are both positive, but still it's just the magnitude, and Tx. And this is the adjacent, this is the opposite. So Tx is equal to T cosine theta, and Ty is T sine theta. And then we are done. Go back to these equations. And now just go back and forth, so you know the Wx and xfx in terms of that. So now we are going to get some relations that between the magnitudes of the forces. So in the x direction, we have, let's look again at the diagram. So you have the tension, you have the F, the N, and the W. And in the x direction, we just have T and F. So just read from the previous table, and you'll see that you get Tx, which is T cosine theta, and minus F. And this is equal to the mass times the acceleration in the x direction. Note that I kept here the component. And in the y, which is now the only forces, there are three forces that have y component. These are the normal minus the weight magnitude mg plus t sine theta. And note that we know that this is 0 because there's no motion in the vertical direction. And once you have these equations, you can solve for whatever the problem calls. If you have the forces, then you can determine the acceleration and perhaps some other motion-related quantities. Or if you know, for example, that the towing is occurring at constant speed, the acceleration is then 0, and then you can find some relation between forces that you're given. So, for example, if the force here, the acceleration was 0, so take the case A equals 0, then you have a relation between the friction and the tension. So you can use that to solve a particular question. So that's the general scheme for solving problems with Newton's second law. Let's just quickly look now at a little bit extra information we mentioned about weight. So remember that weight occurs because the Earth is pulling us towards the center. The ground stops us, but the other pieces of mass of the Earth stops us, but we actually observe this weight down. Now, if we go to the doctor, we actually step on a scale, and let's look at our force diagram. You have your weight and the normal force. Now, the scale is applying this normal force on you, but if you look at the scale itself, you are applying another normal force of equal magnitude, and let's call this N from individual. And the ground is applying another normal force, and there's some weight from the scale. But point is that this scale is acted upon by my normal force and the ground normal force, and this deforms the scale, and this deformation can be read. And in fact, you read it in the form of a number that tells you your weight. So in this case, the normal is equal to the weight, and the normal can be read. And in fact, so we know our weight because we somehow use this normal force to obtain information. However, this changes. So this is your weight, but this is going to change if we, for example, put yourself in an elevator. Now, this normal force that informs us about the weight, we call it the apparent weight. And in the normal case, it's just the weight. But in the non-normal case, when your elevator is perhaps accelerated, if you have an acceleration upwards, then your normal force is going to be larger. N2, and you still have the same weight, but then N2, when there's acceleration, is larger than the weight, so your apparent weight is larger in an accelerated elevator. The last part, I want to remind you that we work a little bit in lecture and will definitely be part of the exam, is this. So there are some problems where you need to consider inclined, and I want to remind you that there's some work to be done, and you can watch the other video that is even more entertaining because it has exercises. So I keep asking you questions, and you keep answering them. And then in this system, what's going to happen is that usually we want to analyze it with an axis along the motion, the direction. That's terrible. With an axis towards the direction of motion. There you go, that's better. So that's my x-axis, and this is my y-axis, perpendicular. And in this case, we typically are going to identify a weight, which points down, and a normal force. And then you might have some other action there. You can have a friction force, maybe, or not, or some tension, or many other possibilities. The problem here is that the normal force is very easy to describe. In this tilted system of coordinates, you have n in the y direction, because that's easy. And the weight is not, because look at it. It is actually sort of neither in the x nor in the y. Turns out that you can determine that the composition of this weight is going to be positive in the x direction, so Wx is positive and Wy is negative. So this is Wxi plus Wyj, and this is going to be negative. Wx turns out to be W cosine theta. Sorry, no, not that one. W sine theta. And Wy is minus W cosine theta. How do I know that? So that was the subject of the other video. You should review it. The short answer is that if you look at this diagram and set a nice system of coordinates here, that's even worse. So you said the horizontal and vertical, but then you also have x and y. And you can show that the angle theta here ends up also here and here. And then obviously this is 90 minus theta. And the angle between y and the vertical, note that they are not the same, y and vertical, make an angle of 90 of theta degrees, just like x and horizontal also make an angle of theta degrees. And that's how we obtain this result. How do you use it? Then you go back to these ideas. You can write your equation of motion. Then using that decomposition, you can write down the final form of the equations of motion, and then use that to determine some interesting properties of the system. This review is not exhaustive. There was, of course, more material covered in lectures. There are some details that I am not reviewing, but you should, of course, know. some because we saw before, and some others because you are good students and you're going to study the material. So you need to go in a little bit more depth, for example, trying to understand what mass is, trying to understand apparent weight, trying to understand some results about projectile motion, for example. So that's part of your work. But I hope that these general comments will help you focus some of your efforts, and you have a good exam. So thank you, and I'll see you in the exam.